Recording started.
Good morning, everybody. I hope you guys are doing well today. That's good. All right, so as far as announcements go, I don't have anything major for you. The Unit 4 test, a couple people have started to take that and turn that in. Amazing scores so far. So I'm really impressed with how the trig unit is going, and we're going to kind of continue that with the next unit here in Unit 5. But very impressed with how the scores are coming out from that Unit 4 test. So um, hopefully, if you haven't taken that yet, just seeing and kind of knowing how the others did, hopefully you can kind of follow suit with that because things look really well. Were there any questions with Unit 4 before you want me to go into Unit 5 here? Okay, then Unit 5 actually is going to be kind of tricky. If you liked geometry with your proving and your proofs, you're probably going to like the start of Unit 5. If you didn't like proofs in geometry, you may not be the biggest fan of what we're going to do here to start Unit 5 off. So we are going to be taking a look at using fundamental identities, and basically what that means is we're going to start off by proving some functions, so some identities. But what we're proving, everything is being done with trigonometry. Okay, so we're working simply with those 6 trig functions. In order to do proofs, though, we need some identities to help us along the way so that we can simplify, hopefully, the process here. So there are a lot of notes that you're going to want to take down, and I don't know if you'll necessarily want to handwrite all of these. If we were in a traditional brick and mortar setting, like we were all together in a classroom, this would be something that I would have printed and hanging on the wall for you to look at all the time. Like, so anytime you wanted, you could glance over and you would see this on the wall in the classroom. So that just kind of gives you an idea of the importance of it and how often you're going to need it. All right. So if you find yourself really struggling with these proofs in Unit 5, I would recommend maybe making some posters to hang around your workspace when you're working on these. It might be a good idea to just whip up some colorful posters and have these identities kind of just staring at you when you're working through your problems. Now, hopefully, you will not need to write down these reciprocal identities or the quotient identities with tangent and cotangent. Hopefully, we have those memorized by now. So, again, remember sine, cosine, and tangent. Um, the reciprocals of those would be cosecant, secant, and cotangent. So 1 over sine, 1 over cosine, 1 over tangent. But the 3 main trig functions can also be written as reciprocals of cosecant, secant, and cotangent. So just note that as we're proving things and trying to simplify things along the way, we may have to use that form as well. Although they don't come up that often, knowing that cosecant, secant, and cotangent, those appear more than the ones below it. And hopefully we already know that tangent is the fraction sine over cosine, and cotangent is the reciprocal of that, cosine over sine. What we do not know yet is how the Pythagorean theorem comes into play with our trig functions. So we can use the Pythagorean theorem with our trig functions, and if we were to bring out our unit circle, we could see that right triangle being created, right? So the book might do a better job of explaining how the Pythagorean theorem comes into play here. So if you have like the unit circle around this triangle here and it's kind of split into 4 quadrants, not the greatest drawing, but you can see kind of see what's happening there. Remember, a point out on the unit circle is from cosine over sine. right? So the cosine value responds to the x coordinate and the sine value correlates to that y coordinate. We also know that the radius of the unit circle is 1. So we do know that fact as well. So using the Pythagorean theorem in that right triangle, we can get the cosine squared plus sine squared equals 1 squared, which is just 1. So if you're wondering where that Pythagorean identity came from, this is the facts behind it. Okay. This is going to be the most common Pythagorean identity that we're going to run across. So generally when we're trying to simplify things, we're looking for a cosine squared plus sine squared, because if we have those together, we know we can replace it with the 1. We can use substitution along the way and replace it with a 1. So that's going to be our goal in today's lesson, is trying to simplify some identities by using some of these rules here. Now we can rearrange these 3 Pythagorean identities and technically have 9 different formats for them, right? Because here I have 1 solved for, but I can also rewrite this where I can solve for cosine squared. How would I get cosine squared by itself? You would subtract the sine squared. So note that each identity that's listed here has 2 other forms that can follow suit from it. So that first one, you can also use the fact that cosine squared equals 1 minus sine squared, and you can use the fact that sine squared equals 1 minus cosine squared. So when I said that there were 9 different identities that you could create here, each one can be written 3 different ways. So hopefully that makes sense now. All right, any questions with the different ways that we can rewrite these identities? So solving for the different terms that are in there? We're going to want to be careful and keep an eye out for these identities. All right, we may not have them memorized completely, but again, that's why I would recommend maybe making a poster to hang in front of you so that as you're working through and simplifying these, if you see like a sine squared and a 1 or a cosine squared and a 1 that are kind of grouped together, that should catch your attention, because you can look at that poster and be like, oh, that's right, 1 minus cosine squared, I can replace that with sine squared, or I can substitute that with sine squared. So having that kind of staring you in the face is really going to help, I think. All right, any questions with the 3 Pythagorean identities before I move to the next slide? Okay, and today may feel a little bit overwhelming. That's totally normal at this point. But hopefully as we continue through and keep using the identities, they'll sink in. So if you're a little bit overwhelmed today, don't panic. That's a normal feeling that you'll have. All right, here's an example that we can use with our identities. It says find sine theta and cosine theta if tangent theta equals 5, and we have the restriction that cosine theta must be greater than 0. So knowing that just kind of helps solidify that sine and cosine are both going to be positive values, right? Because if tangent was positive, then sine and cosine would either have to both be positive or both be negative. But having that extra fact at the end there saying cosine's positive just solidifies that we know the sine value is also going to be positive here. All right, there's lots of different possibilities that we can come up with though, because I know tangent is sine over cosine. And there's lots of different ways that we can have that equal 5. We can do 5 over 1. We can do a 10 over 2. We can make that a 15 over 3. Like the possibilities are almost kind of endless with what we can come up with for sine and cosine. So we're going to need a little bit more to go off of here. And that's where our identities come into play. So let's go back a slide, check out those Pythagorean identities, and see if there's any that deal with tangent. Because if there are, we're going to use that to try to help us narrow down the choices and possibilities for sine and cosine. And we're in luck, right? The second identity listed does have our tangent squared there. So I'm just going to take this and use it on our next slide. All right, and let's replace what we know. We know tangent is 5. So we've got to square that still. So tangent x in our case, or theta, was 5. We substituted that with the 5. So I go ahead and I did that. Let's see, secant squared is going to equal a 26 then, right? Because 5 squared is 25, plus 1 is our 26. Let's go ahead and do the square root. And technically when we're doing the square root, we want plus or minus in front of that. However, we can get rid of the minus sign because we have the restriction for cosine. We know that it's got to be positive value. All right, secant is the same as 1 over cosine. Therefore, cosine must equal what? One over the square root of 26. Now we want to rationalize that because we don't want to leave the square root in the denominator. All right, but we got cosine. Whew, that's not very pretty, is it? All right, once we have the cosine value, we're halfway done. We still want to find the sine value, right? So to find the sine value, I can come back to this fact here that sine over cosine equals 5, right? So I can replace, I'm still searching for the sine, but I'm going to replace the cosine with that square root of 26 over 26, and I'm going to have that equal 5. What am I going to do to solve for sine here? Yeah, multiply by the denominator, right? So that's just going to be a 5 times square root 26 over 26. Whew. Seemed like a doozy, right? But we were able to narrow down all the possibilities for that sine and cosine option to get what we needed there. All right, any questions with that? Okay, it's kind of different. We haven't really seen these identities kind of used like that before. All right, the next set of identities, and again, this is all found in your book, might be a good idea to create posters for it on some pieces of paper. So we have something called cofunction identities, and I don't expect you to memorize all of these by any means. And then we have even, odd, and even identities. So again, these are just listed so that when we try to simplify things, we can use these to hopefully substitute and get our our problem reduced, so to speak, simplified. All right, since I'm not going to make you memorize these, we're going to go ahead and take a look at the next example, and we'll probably just have to flip back and forth. Or if you have your textbook handy, these are in your textbook as well. You can have that open in front of you as we're working through these problems here. The identities are on page 406 and 407 of your textbook. So if you're looking, they're in those blue boxes there. So if you want to have that handy as we work through some of these, that way we don't need to necessarily flip back and forth in the PowerPoint here. Okay, so let's go ahead and look at the next one. It says if cosine theta equals 0.34, find sine of theta minus pi over 2. All right, this is not exactly one of the cofunction identities, but it looks very similar to one. If these were reversed, it would be a cofunction identity. In fact, if they were reversed, what would that cofunction identity equal? So what could I necessarily replace that with? Cosine theta. All right. However, we didn't necessarily have that exact identity written here, but we can reverse the order of what's inside parentheses there. What is needed for us to reverse the order? So if I wanted to reverse the order inside the parentheses so that it read sine of pi over 2 minus theta, what has to be done for us to do that? You have to multiply by a -1. Yep. So instead of having just cosine theta, we're going to have a -1 times cosine theta out in front. Well, cosine theta is the 0.34. So I'm going to replace that with 0.34 in the problem, and we'll get a -0.34 for our answer. So not too bad, but we needed that extra fact that if we multiply by the -1, it allows us to switch those terms inside the parentheses when we're using subtraction there. Questions with example 2. All right, some of the problems are going to ask you to simplify, and factoring should come to mind, right? So sometimes it's a little bit hard to actually visualize that, but if you can replace it with variables, maybe it helps a little bit. So if I do like an x cubed plus x times y squared or something like that, and replacing sine and cosine with just x and y, it can actually help the whole process a little bit. So if you really struggle with the factoring piece, maybe try just rewriting it using variables and see if you get anywhere with that. I'm going to take this away though for now because hopefully we won't need that. When we simplify this, we're looking for a GCF. That's the first step for factoring. So is there a greatest common factor that we can take out between those two terms? We can take out a sine x. When I take out a sine x, I have a sine squared x plus a cosine squared x left. And hopefully that sine squared plus cosine squared, red flags are going up because that's the number one Pythagorean identity that we see. So what can I substitute sine squared x plus cosine squared x with? A 1, yeah. So anytime you have that sine squared x plus cosine squared x, remember that equals a 1. So obviously multiplying by 1 doesn't change what we got there. So this is going to simplify down to just a sine x. So this one wasn't too bad. Questions with that? So we're always on the lookout for those Pythagorean identities. All right, sometimes it'll be in factored form for us, and then we need to expand it to find which identity we want to use for the substitution piece. So here we'll notice that in the numerator of this fraction, we want to expand that secant x plus 1 times secant x minus 1. So starting that multiplication process off, we're going to get a secant squared x. And then I'm going to notice, because these are the same but the opposite sign is used, this is actually your difference of squares, right? That middle term will drop out when you multiply through. So the middle term is gone, and I am left with a minus 1 at the end. All right, we should go back to our Pythagorean identities, because anytime I have like a trig function squared, I'm going to search for my identities here. Now I will have to look at one of the identities and rewrite it to figure out what I can substitute in that numerator. But what can I substitute in that numerator? So secant squared x minus 1, what does that actually equal? Here's the identity that catches my eye. Right? So I need to rearrange this, because I have the secant squared theta, but I have an extra minus 1. But I notice if I subtract 1 from this side, I can get that secant squared theta minus 1. What does that equal? Just your tangent squared, yeah. So I'm going to replace in that numerator secant squared x minus 1 with the tangent squared x. I can then simplify even further, because tangent squared x is the same as sine squared x over cosine squared x, right? And now I actually have a division problem that I can change into multiplication and try to simplify from here. So let's go ahead. I'll make some room on the board. Remember, you cannot divide fractions, so I'm going to change this division problem to a multiplication problem. In order to do that, we've got to take the reciprocal of the second fraction, or that denominator here. So notice I did take the reciprocal when I changed this to multiplication. What can cancel from this problem now? The sine squared x. So then that leaves us with just a 1 over cosine squared x. And 1 over cosine squared x, we can use a reciprocal function for that. What does 1 over cosine squared x equal? Which reciprocal function was that? Secant. Yep. Cosine, 1 over cosine is your secant. Awesome. So we got that all the way simplified to just a secant squared x. Phew, that was a doozy. Questions with that one? Are your brains hurting yet? A little bit. All right, hang in there though. We've got just a couple more things that I want to make you aware of before I send you off to practice these. So once we see some of these examples worked out, and all the different things we should kind of be keeping an eye out for. Hopefully that will help when it gets to the practice problems and the homework. So hang in there. So we talked about looking for factoring. We talked about looking for maybe expanding things like distributing to help us simplify. The other thing we're going to look for is if we're adding fractions or subtracting fractions. So if we're adding or subtracting fractions, what do we have to have before we can actually add or subtract? You must have a common denominator. So that's going to be the goal anytime you see adding or subtracting with your trig functions, especially if there's fractions involved there. We're looking for a common denominator. So I'm going to go ahead and put parentheses around these just so that we know that they're kind of grouped together. What do I need to multiply my first fraction by so that I can work on getting my common denominator? So in other words, what is the first fraction missing that the second one has? Yep, it is missing a cosine x. And then, what is my second fraction missing that the first one has? Yep, 1 minus sine x. Okay, so I'm going to work on simplifying what we just multiplied there. So that's going to give me a cosine squared x. Now don't forget, when I multiply through by the sine x, I am taking the negative sign or that subtraction sign with it, right? We don't want to miss that when we distribute now. So technically that'll be a minus sine x plus a sine squared x. And in the denominator, I'm just going to leave this factored for right now. My hopes is that eventually maybe I can cancel something out if I leave it factored. So do not jump a step ahead here and try to multiply that through as well. Keep that denominator separate because fingers crossed, we might be able to cancel that out with something in the numerator. All right. Does anything catch your eye in that numerator? So it'd be awesome if we could try to simplify that. The minus sine x, okay. What else might catch your eye? Yeah, I think the cosine squared x and the sine squared x catch my eye. So if I rearrange this, because addition is commutative, I can do that, and put those next to each other, what does cosine squared x plus sine squared x actually equal? A 1. Yeah, that's that most basic Pythagorean identity that I said keep an eye out for. So we're going to replace that with a 1. Look what just happened. When I do that, what happens next? You can cancel out with the 1 minus sine x. That's so awesome. That's what we were kind of hoping would happen. That's why we left that denominator factored or split apart there. All right, that's a reciprocal function because you have 1 over something. What's the reciprocal function that equals? Secant. Good. So we can simplify this all the way down to just a secant x. Okay, kind of a lot to take in there. Any questions with that process though, with the adding or subtracting of your fractions to start things off? Okay. It'd help if I had the mic on. All right, so the next example says to find all the values of x in the interval 0 to 2 pi. So that's simply just one time around the unit circle, right? That solves the cosine cubed x over sine x equals cotangent x. Eek! All right, so eventually as we work our way through Unit 5, we will see more of these examples that want us to solve trig equations. All right, so to solve, obviously, if this were just variables and not trig, what would you do? So let's say that the cosine and sine weren't actually there and you had variables instead with x and y. If you saw a problem that said to solve, what essentially would you do? So hypothetical. Something like that. You would try to isolate the variables, right? You try to get them maybe to one side or separate them some sort to help you try to solve that. That's essentially what we want to do here as well. We want to get it equal to 0 so that we can somehow solve for x that's left there. So to solve, we want to get it equal to 0 and then solve for x along the way. All right, so to do that, the first thing that comes to mind is maybe moving that cotangent x to the other side. And as I do that, let's rewrite cotangent x as well. What is cotangent x equal to? So if I want to rewrite that maybe with using sine and cosine, thank you. Hey, that's actually really nice because notice they have the same denominator. So because they have the same denominator, I can rewrite this as cosine cubed x minus cosine x all over sine x equals 0. Now, what can I do to get rid of the fraction? So instead of dividing by sine of x, how can I get rid of that? Multiply by it. And if I multiply both sides by it, I have 0 over here. That's just going to stay as 0. So to simplify this process, let's multiply both sides by sine of x. But when I do that, the right-hand side still stays 0 because 0 times sine of x is 0. Okay, that made our life a little bit easier. What's the next thing you notice to try to help you solve for x and what's left here? Factor it. Yep, exactly. So let's take out that cosine x, that GCF that they have. All right, and we're actually at a point that we can probably solve this using just the unit circle because we do have this factored. Although we could probably break this down into cosine x plus 1, cosine x minus 1 inside there, but I think if we just use our square roots, that will work as well. So we don't have to actually factor using the difference of squares there. But let's set each piece equal to 0 and solve. So let's start with that first piece, that cosine x that we took out. Where does cosine equal 0 on our unit circle? Pi over 2, is there anywhere else? 3 pi over 2. Good. So x is going to equal pi over 2 and 3 pi over 2. All right, the next thing is we're going to do cosine squared x minus 1 equals 0. So let's go ahead and work backwards on that. So we're going to go ahead and it looks like add 1 to both sides. Take the square root. And that'll be plus or minus the square root of 1, which is just your plus or minus 1. So where does cosine equal a positive or negative 1 on your unit circle? Zero and pi. So we're going to add that to our options as well. All right, and we just solved that trig equation there. Any questions with that one? And I'm actually going to refine my answer maybe a little bit. No, it's okay. It does, doesn't it? Okay, taking a look at the time, let's do maybe a couple on our own. So now we've reached kind of that practice part. We've seen all the key examples that we need to keep our eyes on the lookout for. So adding and subtracting fractions, factoring, and then substitution to try to simplify here. So we've got a big list here that we've got to keep our eyes peeled for to try to simplify these expressions. All right, the goal is to get these down to maybe one trig function if possible. That's always kind of the end goal. So looking at the first one, what would you try to do to simplify tangent x times cosine x? Replace tangent with sine over cosine. Awesome. We're still multiplying by cosine x. Ooh, yikes, a little bit crazy with the writing there. All right, then what can we do? I like that first step. Multiply, which means cancel out the cosines. Good. You're left with just sine x. Great. All right, what about the second example? What can we try to do in the second example? Factor. What can we take out then? Cosine x. Ooh, I see a cosine squared and a 1 that's paired together. That makes me think of the Pythagorean identity. Can we replace what's inside the parentheses with anything? Possibly a sine squared or negative sine squared of some sort. A sine squared? All right, I don't think that we can actually reduce that any further or simplify that any further without making more of a mess. So we're going to box this up as our final answer. Even though it does have two trig functions in it, I don't think that we can make that any more simplified than what we have it without making it super, super messy again. Good. Any questions with the first two problems? All right, how about the next one? Sine x times cosecant negative x. And I see, Rebecca, you're typing there, so if you have a question, I can go back. Oh, I know, right? I totally agree with that. All right, that cosecant negative x, that makes me think of those like even odd identities. Maybe we can replace that with something, looking at our even and odd identities on page 407. cosecant of negative x. What does that? Okay, a negative. That helps a little bit. So I can rewrite that and just pull the negative sign maybe out front. So it's not in with the x anymore. So it does help a little bit. What's another thought that comes into mind with trying to simplify this? So Isaias has us on a good start. We can pull the negative sign out front using that even odd identity. But now what? Yeah, use the reciprocal for cosecant, right? That is the same as 1 over sine. What do you notice when you change that to your 1 over sine? Yep. Signs cancel out. You do have the negative sign there, but it reduces to a -1. Awesome. All right, this seems like a trick question, but what about the next one? Sine squared of negative x plus cosine squared of negative x. What is that going to equal? Ooh, possibly using the even or odd identities. It is the Pythagorean identity. Yeah, the only difference is it has a negative sign in there instead of a positive. Is that going to make our answer equal to -1? Or because it's squared, does it not matter? It's always going to equal a +1. Oh, the conundrum. We know it's going to be a 1 of some sort. We just don't know if we should make it positive or negative. We do need to make it positive. Yes. You could use your even odd identities here. I think that would get you the same thing because it would just bring a negative sign out front, but then you'd have to square it, right? So anytime you're squaring a negative, it turns into a positive answer. So we should get a +1 for the result. So seeing that Pythagorean identity, it doesn't actually matter what's inside the parentheses there. It's always going to equal a +1. So it can be any number actually inside there, an x, a negative x, a theta, a fraction, any numerical value actually. So it could be like sine squared of 25 plus cosine squared of 25. That theta can take on any value and it will always equal 1 in the end. All right, let's sneak one more in for today. We have this one or this one. Yeah, let's do this one. All right, that pi over 2 automatically catches my eye. I think that's a cofunction identity, so let's try to replace that tangent pi over 2 minus x with something. So looking at our cofunction identities in our book, what can we replace that with? A cotangent. All right, that's at least a start. The next thing we notice is what? What do we notice? The cosecant x. Did you want to try to simplify that with the denominator? Okay. I like that. We can do that. Makes things a little bit more simplistic for us, right? So canceling out a cosecant x from numerator and denominator. Then what? Then what catches your eye? What can we try to do now? Yep. change cotangent to cosine over sine, and also cosecant to 1 over sine. I'm going to do both of those, yeah, like Isaias had mentioned at the same time, but I know that Tommy and Isaias both kind of came up with the cotangent there. Anything you notice once we rewrite it like that? He did have to one-up you. What are we going to cancel? You're right. What are we going to cancel? The sine of x. Yep, they have the same denominator, so those can cancel. Cosine x over 1 is just a cosine x. Yay! Can't get much simpler than a cosine x, so we're going to call it good and stop there. All right. We had a really good start there, so some good practice. Any questions with what we looked at today with our identities? Yeah, all of our identities. So Pythagorean identities, cofunction identities, even odd identities. Any questions with those? Okay, then in addition to the 5.01 homework assignment, I'm going to task you with also creating some posters for these identities so that you have them to look at as you're working through Unit 5. So these identities are not just going to stop with Lesson 1. They're going to follow us through all the way to the end. So they're not going to go away. In fact, we're going to just keep adding to them. So I'm going to task you with creating those posters that you should use for the rest of the unit as well, because I think that will help. If there's more, there might be a couple more, not too many, but there's some other formulas that we're going to add to the mix. So there's not really more identities, but just more formulas that are going to come at us. So I guess we got that going for us. All right, that's all I got for you though today, so I will let you guys go if you don't have any additional questions at this point. Good luck with the 5.01. Good luck on your Unit 4 test if you haven't taken that. I will start out Tuesday's class next week with taking any questions from 5.01 because I know that these can be a little chaotic and cause some troubles early on in the unit still. So if you are struggling with the simplifying process here, don't panic. Just bring your questions to class on Tuesday and we'll start out with those. All right, that's all I got for you guys. Have a great weekend and we'll touch base again on Tuesday. Bye everyone.